Okay, so am I audible?
Yeah.
Okay, fine. A very good morning to one and all present here. It is a great pleasure for me to welcome you all to the 11th edition of Alumni Research Talk organized by Computer Science Association BITS Pilani. Computer Science Association is a departmental association for the Department of Computer Science. CSA stands as a powerful learning platform with substantial inflow of guidance and mentorship from seniors. The association has an open nature, thus allowing the convergence of computer science enthusiasts from all the streams of study. CSA is noted for organizing quizzes and coding events around the year, innovative events such as anti-coding and capture the flag during Apogee as well as Alumni Research Talks. The first edition of ERT was held in the year 2012, and after its tremendous success, it has continued as an annual event. We are here for the third talk of 11th edition of ERT, and the speaker is Dr. Shikhar Vashishth. He completed his bachelor's degree in information system from BITS Pilani campus in 2016. Post that, he completed his master's and PhD from IISc Bangalore with a thesis on neural graph embedding methods for natural language processing. He has interned at Microsoft and Google Research, and he has received a prestigious ACM Indian Doctoral Dissertation Award and Google PhD Fellowship during his PhD. He was a postdoc at Language Technologies Institute (CMU) in information extraction in biomedical domain. He is currently working as a postdoctoral researcher at Microsoft Research. Over to you, sir.
Yeah. Thank you, Josh, for introducing me. So I'll share my screen. Is my uh, Josh? Can you confirm that?
Yes, sir.
Okay, fine. Yeah. So hi, good afternoon, everyone. My name is Shikhar Vashishth, and I'm currently working as a postdoctoral researcher at Microsoft Research. So today I'm going to talk about my work on improving medical entity linking with semantic type prediction. So this work I did during my postdoc at Language Technology Institute, Carnegie Mellon University. So let us first understand what this problem is all about. So this problem is like in formal terms, it is called as medical entity linking. So it's an NLP problem, natural language processing problem. So here our input is any piece of text. So like it will be a paragraph, and like it can be anything. Like it can be a long document, a small paragraph, anything. And our output would be this. So basically, we would be identifying the relevant mentions in this given document which are related to biomedical domain, and have to link them to some knowledge graph. So I am going to explain all of these terms, but basically we will be given this like a blank like any piece of text, and we have to identify these relevant mentions and link them to some knowledge graph. So for instance, over here the machine is able to understand that low back pain actually refers to some concept in the real world. Similarly, over here, this refer to some concept in the real world. So basically, this is very helpful for machine to understand the text better, because if the machine knows that we are talking about lower back pain, then it can get some more information about it and can understand this text better and can perform further operations on it much better, like than just looking at as a piece of text. So that's what we are solving over here. So just briefly explaining you what is knowledge graph. So knowledge graph, basically it is a way of storing knowledge in a graph format. So it's like a regular graph, so where the nodes would be real world entities, like real world things, basically like people, person, diseases, symptom, anything can be the nodes of this graph. And edges encodes facts. So basically, suppose we have like this small knowledge graph over here. So here John Lennon, Beatles, and Liverpool are the nodes, and the fact that John Lennon was born in Liverpool is encoded through this edge, which is coming from John Lennon to Liverpool, and it is marked as born in. So basically, like that, we can store all the facts of this world in this graph format, and it is And we do not notice it, but this is like very prominent in Google searches. So if you search some person's name, then we get a box on the right hand side. So this box comes from the knowledge graph. So this is the output from the knowledge graph, and it like tells you what all are the related people. Suppose like you search for a person, then what are the related people like of this person, and like that, like more information you get from this knowledge graph. And it is like heavily used in question answering. So this is like an very famous example of IBM Watson, where these people developed a machine which can query these knowledge graph and can answer several types of question, and this was able to outperform even humans on some challenge like Jeopardy challenge. And these knowledge graphs also come into picture in dialogue system. So as you must have seen that several websites are providing chat, and where you can for instance like airline website are providing chat where you can ask questions, cancel flight through the chat format, and sometimes these are automated as well. So for those automated chats, like internally they are making use of these knowledge graphs for answering your questions. uh, and it is also used in web search. So as I told you, like when we search something on Google, then we get some more information about that person, or like any place, anything on the right hand side, which is also an output of a knowledge graph. So in this particular talk, we are going to focus on medical knowledge graph. So knowledge graph are in general, they talk about like they capture everything, say like person, city, all of the things. But we are going to focus in this presentation on medical knowledge graph, which will have entities related to biomedical field. So an instance of it is UMLS, Unified Medical Language System. So this knowledge graph was developed and maintained by NIH, National Institute of Health, which is like an organization in United States, and it is being maintained since 1978. And since then, like it is being improved with time. And the present version has around 4 million medical concepts, which are like collected from 133 different sources, more than 133 different sources. So basically this will include all types of diseases like tuberculosis, even COVID-19, and what are the symptoms of those diseases. So those all like facts about it, what medicines cure the tuberculosis disease. So those kind of facts are and will be encoded in a graph format in this UMLS. So it's a very famous knowledge graph in medical domain. And good thing about this graph is that all the concepts in UMLS are categorized into 127 categories. So there are categories like diseases, symptoms, like that. Like there are several categories, and all the concepts which are there, more than 4 million of them, they are categorized into one or more of these categories in this knowledge graph. So let's understand like how much challenging is the problem of medical entity linking. So basically, as we looked at it, so we will be given a piece of text, and we have to identify the mentions and link them to one of these 4 million concepts in the UMLS knowledge graph. Since we are talking about medical entity linking, so I am taking UMLS as the knowledge graph, with which we want to link our mentions to. So the first problem is, suppose we are able to solve the first problem of identifying the mentions correctly, but the next problem of like linking that mention to one of these 4 million concept is a very tough problem, because we have a very large search space. Like any mention can get linked to any of those 4 million concepts, which makes it very challenging. Moreover, there is a lot of ambiguity in medical field. So for instance, if you have a mention called cold, like then it can refer to cold temperature, it can also refer to common cold, it can refer to cold brand as well. So this homonymy and polysemy, they add a lot of ambiguity and makes this uh, task even more challenging. And like the concepts in UMLS are very very diverse. So they range from living entities to food items, because those also are related to medical domain. So these kind of things are also included in those 4 million concepts which are there in UMLS. And another challenging thing in medical entity linking is that there is dearth of training data. So in medical domain especially, there are a lot of like privacy issues, Like people do not want to share the data because it contains some personal information, and there are several other factors. So therefore, and like moreover, like hiring people for annotating the data is also very expensive, because one has to hire some doctor or some expert in the medical field, uh, whom one has to pay like a lot of money for getting some annotated data. So the largest data set which is available for medical entity linking is called as med mentions, and that data set also covers just 1% of the concepts which are there in the UMLS. So even though like this data is publicly available for everyone, but still it is very very small for training like a good medical entity linking system. So let's look at what people have done in this domain till now. So people have been trying to solve this problem since 2001. So this first method system which came up was MetaMap, uh, and after that, like there are other methods like CTAKes, Quick UMLS, MetaMap Lite. So the common thing about all of these approaches is that they are all based on dictionary lookup, and they follow this kind of pipeline. So given any paragraph, we first perform mention detection. So basically we from this we get this as the output. So here we have all the mentions detected, and our next step would be to link these mentions to some concepts in the UMLS. So that would be the next step. So basically this problem is broken into two steps for simplifying it. So first we focus on identifying the mentions, and then we focus on linking them to some standard knowledge base. So yeah, so most of these things are done through string matching. That's what these approaches are doing. So they have the list of all the entities in the UMLS. So they perform some kind of string matching and try to solve this problem. So the most recent one called as MedLinker, which came up in 2020. That's the kind of first approach which uses neural or deep learning for this particular problem. Yeah, so what we are proposing in this work is that we want to keep the mention detection step as it is. So given any document, we will run the same standard mention detection methods which were being used earlier to get this as the output. So we know all the mentions which are there in the document. But what we do is that we break this entity linking step into two parts. So first we perform some kind of mention disambiguation, and then we perform entity linking. So basically we do this because any mention which has got detected can get linked to any of those 4 million concepts which are there in UMLS. So that makes this problem very very challenging. But if we do mention disambiguation first, then that as we will see later in this presentation, that drastically reduces the search space for each mention. So basically for each mention, we would, instead of having 4 million as our search space, we would have like few thousand as our search space through this step. And that way, like, we will make this problem simpler and will be able to solve it with much more efficiency. So that's the overall motivation of what I'm going to talk about in this presentation. So basically, our main contributions are as follows. So we uh, analyze like how much impact is this like breaking step has. So if we break this anti-linking step into two parts, like first doing this mention disambiguation through our module which we called as med type. So so how much effective this approach is, and how much it reduces our search space. And this is actually done through identifying like the semantic type of each mention. So I'm going to talk about it in the next slide. So apart from this, analyzing the effectiveness of med type, I'm also going to talk about the two data sets which we create for this particular task. So as I told in the last slide, that there's like dearth of training data for medical entity linking. So for solving that problem, we propose two large data sets which are like 3 times, and second one is 164 times bigger than the largest ever, like the previously largest medical anti-linking data. So these two data sets like we create and that I'm going to talk about, and they help us a lot for improving performance on this particular task. So basically at the end we will show that our med type module, which is trained on these two data sets, how much effective it would be for improving medical entity linking. Yeah, so please feel free to ask questions in between, because the presentation is going to be um, a bit long, so you might lose the context or might forget about the things which you want to ask now. So feel free to interrupt me. Yeah. Okay, so this is like an overview of what we are proposing. So basically, we have created this module called as MedType, and this is trained on two data sets which we have created, Wikimed and PubMed TS. Uh, and what we show over here is that we can take any existing like medical entity linking system, and we can combine our module MedType with that system, and it will perform better than the original version of that system. So that's the uh, main contribution, and we can test it on. We have tested it on on several data sets, and we have found out that any information extraction toolkit for medical entity linking combined with our module, it performs better than its original version. So what is this piece that we are going to talk about next? So internally, that piece looks like something like this. So what we are doing actually is that, suppose we are given some text. So over here, for an example, I'm giving that symptom of cold includes cough dash dash dash. So it will be like a long document, but it starts with this: symptom of cold includes cough. So if you give this text to any entity linking system, then it will be able to identify two mentions over here. So one would be cold and another would be cough. So as we know, like a cold can occur in several entities, so it will generate these kind of concepts for this mentioned cold, like cold temperature, common cold, cold therapy, and similarly, cough, it will generate like cough X relief, some medicine, and some cough symptom as well. So what we do is that for each mention which has got detected using the entity linking system, we try to identify its correct semantic type. Semantic type, basically we identify its correct category to which it belongs. So for instance, over here, if we are able to figure out that cold over here, based on the context of this mentioned cold, that it actually refers to a disease or syndrome, then basically we can rule out several candidates which has got proposed, like from this anti-linking system, that we can directly remove cold temperature and cold therapy because they are not diseases. So, and this common cold only would be remaining, and that is our correct answer for this particular mention. And similarly for cough over here, if we are able to figure out that this cough actually refers to some symptom, then we can remove this medicine cough X relief from our candidate list, and we will remain with the correct answer for our mentioned cough here. So that is the overall thing, like what we are doing. So if so basically the main contribution is, like, instead of directly trying to link this mentioned cold to the common cold entity in the knowledge base, we first want to identify its correct semantic type. And once we have got its semantic type, then we don't have to think about linking this particular mention to one of those 4 million, because we know that it has to be a disease or symptom. So instead of 4 million, it will become some thousand or something. So now we have to link this cold mention to one of those thousand diseases which we have in the UMLS. So that's why, like, it is drastically reducing the complexity of the problem, and that way, like, it increase the overall performance also on this task. Yeah, so for doing this categorization, identifying the semantic type of each mention, we use something called as BERT. So BERT actually has become the very famous, or like most used method in natural language processing. So So I will not go into much details about it, but if someone is interested in natural language processing, then one should read about this model. So overall, it's a very simple thing. It's not a very complicated thing. So basically, what it does is that it takes in a sentence or like any document as input. So over here, we have given a document like help, Prince, Mayuko something. So and you can assume it for now. You can assume it as a like a black box. So it will take in any text as input. And if we are solving like a categorization problem, so at the end it will give us a vector representation of that entire sentence. So basically, like a list of floating point numbers, it will give us. Given any text, it will give us like a vector of floating point numbers. And the good thing about those that vector is it encodes all the semantic meaning of that sentence. So the entire gist of that sentence, summary of the sentence, whatever you call it, like that is encoded in those floating point numbers. That's the good thing about it. So it does it quite well. So internally, how it works, how it is trained, those things are like secondary. But these systems, like they are available pre-trained, so you can just use them as a black box. That's what we do in this particular one. So we just use it as a black box. We give our mention and its context as the input to this BERT model, and it gives us a vector representation for that mention, and that vector we give to a classifier. So classifier is nothing, it's just like multiplying it with some matrix and adding a bias like that. So simple feed forward classifier, and that tells us whether which category this particular mention belongs to. So over here, like for example, I'm just like listing spam and not spam, so it's like taken from some source. So they have given this example, like identifying this email as spam or not spam. So that's the problem they are solving here. But instead of like solving this binary classification, we have like a multi-class classification problem there. So our instead of like these two categories, we would have like all the semantic types as our classes, and we want to identify each mention among those one of those classes, like categories which we have. So that's how like the model looks like. So looking at it once more, so basically this box which I'm talking about here, this is what BERT model is. So we feed our mention with its context to this BERT model, and it gives us a vector representation, that list of floating point numbers, and that is given to a classifier, and that classifier tells us like the correct semantic type of a given mention. So this is how it is done. So for instance, our mention is standing flexion in this particular case. So we will pass say like 10 tokens before and 10 tokens after this particular mention standing flexion, and we'll pass this whole thing, like the thing which is like marked with underline, to our BERT model. That will give us a vector, and that vector would be used for classifying the correct semantic type of this mention. So in this case, model has told us that this belongs to diagnostic procedure, and suppose like this, for this standing flexion, if suppose this is our list of candidates which has got generated through some entity linking system, and once we know the correct semantic type, then a lot of them would get ruled out, because they do not belong to a diagnostic procedure. So therefore a lot of candidates which got proposed for this mention, they have got ruled out. So that is how like our model is working. Yeah, so that was the whole thing. That was the main contribution which we did. So using this simple classifier which was based on BUD, we tried to disambiguate the correct semantic type of any of a mention which was detected using some entity linking system. And once we know its correct semantic type, then we were able to rule out the candidates which were generated uh, for that particular mention. So now I'm going to talk about the data set which we created for medical entity linking. So we used Wikipedia for creating this data. So we downloaded the entire Wikipedia corpus. So Wikipedia, I think everyone uses. So if you would have looked at like a bit more cautiously, then you must have noticed that in Wikipedia there are these hyperlinks as well in any given article. So we took all the Wikipedia articles and we made use of these hyperlink information for creating our data set. So basically these hyperlinks, they point to another Wikipedia page. So that is how whole Wikipedia is created. So what we do is that using other knowledge sources like Freebase, NCBI, Wikidata, so they are all like other kinds of knowledge graph. So we get this information, we get a mapping from Wikipedia page to concepts in UMLS. So as you know that in Wikipedia there is a page on tuberculosis, and in UMLS also the knowledge graph, the medical knowledge graph which we are working with, that also has a uh, node for tuberculosis. So we just got this mapping like Wikipedia page to UMLS concept. So that's the mapping we got. For instance, like Mycobacterium tuberculosis is a page in Wikipedia, and Mycobacterium tuberculosis would be an entity, would be a concept in UMLS as well. So we are just getting one-to-one mapping between these two things. So once we have that through these sources, then basically what this paragraph will become our data, like on which we can train our model, which we talked about in the last slide. So what will happen is that suppose like we have tuberculosis here. So tuberculosis, suppose we have tuberculosis page in Wikipedia, like hyperlink to tuberculosis over here. So that from that page we can get UMLS concept. And as I told earlier, that in UMLS every concept is categorized into 127 semantic types. So that UMLS will tell us, the knowledge graph will tell us, UMLS knowledge graph, that this tuberculosis actually belongs to disease and syndrome. Similarly, over here as well, Mycobacterium tuberculosis, that will we will get like a UMLS concept for this particular hyperlink, and UMLS will tell us that the semantic type of this particular mention is a bacterium. So now once we know that this particular mention, its type is a bacterium, then based on its context, our task becomes like we have to predict back this category. So basically the training data would be, we will have Mycobacterium tuberculosis as I mentioned, and uh, we will give the whole context, say like from tuberculosis till to body as the input to the model, and our task would be to predict that Mycobacterium tuberculosis belongs to bacterium class. So that is how like we are creating the training data for one model. So Wikipedia, using Wikipedia, we are creating this data set. So it's like a very common technique. So people download like entire Wikipedia and they use the hyperlink information for creating data sets using it. So overall, from these knowledge sources, NCBI, Freebase, Wikidata, we get mappings for 60,000 Wikipedia pages to UMLS concepts. And here again, like I'm just showing how we create the data. So suppose we have this Mycobacterium tuberculosis. So we know it's mapping to concept in UMLS knowledge graph, and UMLS will also tell us what is the category of this. So we have the mention, we know its category. So based on it context, we want to predict its category. So that's how like the training data is getting generated. So this will be our X, and the Y would be, the label would be bacteria. Input would be this whole piece of text till here, like from tuberculosis to also. That's how like the data is getting generated. So overall, we make use of around 400 pages in Wikipedia, and we get around 1 million training samples using the entire Wikipedia corpus. And since we know that in Wikipedia, all the pages are written by humans, and there are a lot of editors as well who keep on checking whether the information is correct or not. So therefore we can assume that most of the information there is correct, and links there have very high precision. So that's what our assumption is. If someone would have made mistake there, then that noise will come in our data as well. But for this data set, we assume that those kind of mistakes are very, very rare. And actually it has been found out also. So there are papers who have done manual evaluation of all of the pages, and the accuracy of these hyperlinks is around 97%. So that is like quite good. So overall, we get these numbers. So as you can see over here, we get much larger data set. So med mentions, before our work, med mentions was the largest publicly available medical entity linking data set, and it has around 4,500 documents, and 42,600 sentences, 350K mentions. So compared to that, we get like a much larger model using this Wikipedia. So overall, we get around like 3 times larger. So this mention is basically what we see for comparing different data sets. So overall, we get like 3 times larger data set using Wikipedia, and without putting any money like in this creation. So like Wikipedia is freely available, anyone can go and download it, and using some these kind of tricks, we created like a data set for free for medical entity linking. So that's what our contribution was. The second data set, sorry, yeah. Yeah, the second data set we created was using distantly supervised learning. So everyone, I hope most of you must be knowing about supervised learning. So in supervised learning, we are given some input and we know its correct label. So that's what we know about like supervised learning. So there is something called as distantly supervised learning. So it's a variation of supervised learning. So here the main difference is that the labels will not be 100% correct. So there can be some noise in the label. So suppose like you know like given x, so its y can be wrong, can be correct as well. So there is some ambiguity, but most of the time it is correct. But in some cases there is a lot of noise as well. So so this technique basically in distantly supervised learning, the data sets are created automatically using some external knowledge source or heuristics. So it elevates the problem of lack of annotated data. So basically like you don't have to pay people to create the data, don't have to pay the experts to creating the data. Like using some external source, we have got a data, we have got some data where the labels might not be correct like 100% of the time. So that is like one caveat of this, but it is heavily used in relation extraction. So this is like another problem. But from there this particular thing came up. So in 2009, Mintz et al proposed this distantly supervised learning idea. So what these people did was that so in I need to like briefly describe what is relation extraction. So relation extraction is also another problem in natural language processing. So here basically the task is you are given some piece of text and you want to extract facts out of it. So for instance, if you are given this sentence, Trump US president addressed the people. So from this sentence you can extract fact that Trump is the president of US. So it's like a old thing now. So if Biden is here, so Biden is the president of US. Yeah. So that's the fact you have to extract from this sentence. So that is the relation extraction task. So what Binz et al did was that uh, he created a data set. Suppose like he already knows this fact that Trump is the president of US, or Trump was the president of US. Then basically what heuristic he proposed for relation extraction was that if in any sentence you see Trump and US, then from that sentence you can extract that Trump is the president of US. So that's how like we work in distantly supervised learning. So my assumption is so his assumption which we proposed in 2009 was that if any two entities uh, uh, have a relationship in KB. So for instance, basically he wants to say like if we know this fact that Trump is president of US, and if there is any sentence which is mentioning Trump and US, then that sentence expresses this precedent of relationship, like precedent of relationship between Trump and US. So as you can see, this assumption is not 100% correct. So for instance, if you have this sentence, Trump was born in New York, United States, Okay, so this sentence actually does not convey this information that Trump is the president of US. But uh, most of the time, like in this first sentence, in the second sentence, it is actually true that these two sentences are representing this precedent of relationship between Trump and US. So that is what like heuristic is. So like um, uh, one third of the time it is wrong, two third of the time it is correct. So that's how like we create the data. So now basically this has become our data set. Now from this sentences, like we have to extract back this fact out. So like using these sentences, we have to find out that Trump is president of US, like that. So this is how like the data set is created using distant supervision. So this actually works really good in real life. So if we have like a bunch of these facts, then we can create a very large data set, and we can train our model to extract back that fact using the sentences which we have generated, and that way like we will be able to train a model which can extract new facts for us as well in the future. So yeah, so that's what the motivation of us was for creating this second data set. So what we do over here is that so we make use of something called as PubMed. So PubMed actually is just like we have Wikipedia. Similarly, we have PubMed. So PubMed has like collection of all the scientific papers which have got published in the biomedical domain. So whatever papers have got published in the biomedical domain, they uh, are part of this PubMed corpus. So so as you know, like every year a lot of papers get published, so it's a very large corpus. So overall the current version has around 22 million documents, like 22 million scientific papers. So it's like a huge collection. So what we did over here was that we took abstract of all the papers, all the 22 million papers. So that's what I'm showing over here on the left. So we have abstract. So I'm showing for one paper. Yeah. So this is like the abstract of that paper. And the good thing about this PubMed article is that for each paper they also have a list of headings. So basically for this particular paper, the heading, like the mesh headings would be bacilli and pulmonary tuberculosis chemotherapy, like that. So so these mesh headings, you can assume it as keywords, important keywords in a given document. So if someone has read any scientific paper till now, then people might have noticed that in computer science also, in any paper, after the abstract we list down some important keywords in that particular paper. So this is like followed in uh, several conferences and journals. So that's what so this is like mesh headings are kind of equivalent of that in the biomedical field. So what we do is that we identify the mentions which are uh, part of this abstract using some biomedical NER system, named entity recognition system. So basically you can just look at it as a black box. So it takes in the text and it identify the mentions which are relevant mentions which are part of this abstract. And over here what we do is that, so these mesh headers, they come with some unique ID, and these IDs are directly mappable to UMLS, and UMLS can give us the semantic type of these headers, like which are part of these mesh headings. So now what we do, over here you can see that bacilli is there, and for bacilli we know its ID, we know its UMLS ID, and we know its semantic type. So bacilli semantic type is bacterium, and this bacilli is occurring over here as well in the abstract. So that's how like so we can directly do this mapping. So from bacilli we know that its semantic type is bacteria. Similarly over here, pulmonary tuberculosis is mentioned, and pulmonary tuberculosis is in header as well, mesh heading as well. And we from UMLS through this like chain of like mapping, we know that the semantic type of pulmonary tuberculosis is disease or syndrome. So that's how like we are getting this information. So like we are able to link pulmonary tuberculosis to disease or syndrome. Similarly, chemotherapy has got linked to therapeutic therapeutic procedure, like that. So this is how like the data is getting created. Now we can create the data using it. So basically this is our mention, and we know its semantic type. Now our data would be like looking at its context. We want to predict back this semantic type. So like that, we are creating the data just like we did in the wiki from the Wikipedia. So now we have got these hyperlinks in this particular abstract. So in real world, this looks something like this. So each PubMed article appears like in this format is called as XML format. So this is a very famous format. So even our web pages are written in this kind of format. So as you can see that this abstract is present over here, and these mesh headings are listed along with their IDs. So over here we can see simvastatin is one of the mesh headings, and it is occurring over here as well in the abstract. So we can directly get the from this ID we can get the semantic type of this mention, and like that we are creating the data set. Yeah, so as I told, like April 2020, the size of this PubMed corpus was around 20 million. And after this whole processing, we get around 58 million mentions, 58 million data points basically from this PubMed DS corpus. So if you look at the numbers now, so this bed mentions was the previous largest publicly available medical entity linking dataset, and it had around like 350k mentions. And now we have got 58 million size dataset. So it's around like 163 times, 164 times larger than med mentions. So as you can see, like it has these datasets are really big compared to the earlier datasets. And like basically now the idea would be the model which we talked about, the bird based model which we talked about, we will train on these two datasets, and then we'll use it for medical entity linking. So since we created this PubMed DS dataset using distant supervision, and in distant supervision, as we know, the labels can be noisy as well. So we had to do some manual evaluation of our data to check its quality. So we tested it on these three datasets, which are all manually annotated through medical experts, and we found out that overall we get these numbers: precision and recall. So we can see that precision is really good. So on an average we get around 84% precision, which is like really good for distant supervision. Although the recall is very poor, so recall is on average around 3 or 4%. So recall actually does not is not a very big issue for our case, because we are dealing with 20 million articles, scientific papers, and even if we have like 4 to 5% recall as well, but because the data set, the corpus is so big that this 3 to 4% recall also gives us 58 million mentions. So therefore, like, we do not worry about recall, but precision was really good. So that's why like this data set is useful for us. Like if precision would have been like 30% or 20%, then this data set would have been useless, because most of the time like it contains noisy labels. But 84% is a good number for distance supervision. Yeah, so these are like some numbers, but just focus on these red boxes. So I'm just listing like how much coverage we are getting. So basically this is like the stats of these data sets, like how many mentions it contains for different categories. So for instance, how many mentions for disease or syndrome, how many mentions for uh, pharmacological substances, like that. So we can see that these numbers are increasing many folds. Like, so from 11,000 we have come to 9 million. So we have like a huge data set to train our model on. That's what I wanted to say in this particular slide. Yeah, so for experiments, we evaluate on these four data sets. So so these are all four data sets are manually annotated by experts. So like doctors and medical experts have like group of them have sat down and created these data sets. So this NCBI has around like 793 PubMed abstracts manually annotated, and similarly over here we have 1500, and these are some like clinical notes which are annotated, and it mentions like 4500 around abstracts are manually annotated. Yeah, that's the data set like which we work with. So these are the results. So I know like there are too many numbers over here, but basically these are all the previous approaches for identifying the semantic type of any given mention, and this is the numbers after this line is the performance of our method. So basically, if you look at the this number, the first row, med type, then here we can see that in 3 out of 4, so leaving the first one, in 3 out of 4 we are able to perform better than the previous method. So this basically shows the effectiveness of BERT. So none of these previous approaches use a BERT based method. So basically this shows that using the BERT model itself is very effective for identifying the correct semantic type of any given mention. And over here, basically, I am showing that if we train our model on this data set, the first data set which we created, Wikimed, and then evaluate on this problem, then we get some improvement. So like that, so we got like 3% increase in accuracy. Over here also 3%, and here 1%. If we train on the second data set, then we get like slightly more increase. And if we combine both of them, like if we train on Wikimed as well as PubMed TS, so that's what this last row is. So if we combine both of them and then evaluate on this task, then we get even more higher number. So like a combination of both the dataset works the best, and it has given us like 97% numbers as well, which is like really good for this particular task. So from 90% we have jumped to 97% on some of these data sets, which is like a great improvement. So this basically shows that the data sets which we have created, that is like very helpful and is really useful for this task. Yeah. So if you look at like on some of the categories, so for instance, on detecting disorder category in any data set, so the numbers are increasing from 39 to 74, so like that. So this is like the different versions of our model. So this one is trained on Wikimed, this one is trained on blue one is trained on PubMed TS, and this is like the plain model, not trained on any of these data sets. So we can, as you can see that over here, in training using these data sets which we have created gives us like a great improvement in performance across different settings. And now we are going to do our final evaluation. So this was our idea. So we are proposing this piece, this module, which we are calling as a med type, and it is trained on the two data sets which we created, one from Wikipedia and another from distant supervision. So we have this module ready, and now we want to check if we take any information extraction toolkit, and if we combine our module with it, then whether it performs better than it or not. So that's what we are going to evaluate next. So yeah, so we compare the default performance of any entity linker, and then we compare it with how it performs when we combine it with our method. So that's what the met type is. And over here we also evaluate like an oracle setting. So in oracle setting, basically we are doing some kind of cheating here. So this is just for getting to know like what is the upper bound performance of our model. So basically what we do over here is that we look at the ground truth label for every mention, and we directly provide that type information to the model. So basically this is just for getting the upper bound, like the best case performance for entity linking, for entity typing for entity linking, like that we are doing. So I'm just showing it for one of the information extraction toolkit, size spacey. So if you look at the default performance of SciSpaCy, like just so this is like a publicly available model, so anyone can download it and run it on these data sets. So this is like the performance of this model, and if you combine it with our module met type, then we get like 3.8% improvement over 56.0. So like that. So it is like consistent improvement across these data sets, and these are like upper bounds. Like the maximum improvement which you can get if our met type would be giving 100% performance on entity typing, like detecting the semantic type of any given mention. So we can perform very comparable to the Oracle as well in this setting, and overall you can see that we get around like 3 to 4 to 5% increment as well if we combine an entity linker with our system. So yeah. So I think that was it, like all the results. So I'm not going into more detail, but our code is available on GitHub, so anyone can go and look at it. So apart from code, we also provide a service for this particular module. So basically, it is based on BERT as service. So it is just for like scaling this. So if someone wants to run it at scale, like annotate thousands of sentences per second, like if someone is using it in industry or somewhere, then also like this particular model is scalable, and we provide support for all the existing entry linker systems. So you can provide the correct linker, and like you can choose basically what linker you want to use, and based on that you will get the output. And it is like installable using like a simple pip command. So you can just go to the repo and just do simple pip install, and it will directly download everything which is required, and you can run it. So overall it looks like this in the code. So you just need to import uh, just this met type client, and need to provide the text which you want to annotate, and at the end like you will get the output. So we also provide the code for training, like to reproduce all the numbers which I have shown in this presentation, and evaluation code is also included, and everything, and the data sets which we create are also available in this JSON format, like easily readable JSON format, which anyone can understand. So these data sets are also publicly available. So this actually, I had a very nice demo as well for this particular. So one can go to mettype.github.io. So currently it is down because I am not at CMU anymore. So I'm not able to maintain like the server for hosting it is in CMU, but I'll talk with people to get it working after this presentation, so that like you people can also try it out. But basically this is how like it looks like. So actually the dummy thing is still there. So this is how it looks like. So you can provide any text over here, and you can choose like what entity linker you want to choose, and we have like 3 variants of our model. uh, General text, like this is for normal text, like, which is there on Wikipedia, and which you write in your day-to-day life. And then we have like specialized model for biomedical research. So in like papers, scientific articles, people use a different kind of language, so we have a separate model for it. And then the third model is for health records. So in health records, another kind of format is used for writing things. So for that we have another type of model. Yeah, so one can actually run it. So currently it will not work, so I need to uh, do something to get it working. But basically it looks something like this. So if you uh, press start, then it gives you this fancy kind of output. So basically what it has done is that it marks all the mentions which is it has detected, and these different colors actually refer to different semantic type. In this purple color, disease or syndrome mentions have been listed, and in red anatomy is there. So like that, it shows the output, so one can look at it where it is failing and can work on further improving our model. So actually the code for running this demo also is provided in the repository, so you can download it and run this thing locally and can try it out. So it will be more faster because uh, we cannot, so it's not our server is not very powerful one, so it cannot handle multiple requests, and moreover it crashes also most often, it has crashed today as well. So yeah, so I think local version would be a great option to test it out, like how well it is working. So yeah, so that's it. So this work has got accepted at two places. So uh, it has got accepted recently at Journal of Biomedical Informatics, uh, and medical this AMIA conference, American Medical Informatics Association, and this is in collaboration with Rishabh, Dennis, Ritam, and Carolyn. So Rishabh is actually like a BITS graduate from Pilani campus, so he was passed out uh, from I think 2018, and he was working. He was doing his masters at CMU at that time. So and there I got to collaborate with him. So yeah, so in conclusion, basically we talked about a system called as MedType, which is for which basically shows that disambiguating mentions and then doing entity linking is much better than directly doing entity linking. And we show that it is very helpful for this particular task. And we also talked about two large data sets, Wikimed and PubMed TS, that how they were created and how much effective they are for medical entry linking. Yeah, that's it. So this work was actually supported by uh, NSF and Dow Chemical and UPMC. So as well, those people have kind of funded this project. So I'll be happy to take questions on this particular work.
Hello. So there are some questions asked in QA section.
Yeah, I can see them. Um, okay. Yeah, so the first one from Chaitanya Bala. So his question is, what are the pros and cons of corporate research over PhD or university research? So the pros are, in the corporate we have more computational resources available. So we have more number of GPUs, which is very essential for running deep learning experiments. So we can train basically bigger models. We have these companies like Microsoft, Google. They have in their own internal data sets which are not publicly available. So we get to work with more bigger data sets, which we'll never get to see outside. So that way, we can see the actual potential of how much machine learning, how far machine learning can take us. The cons of corporate research is that generally some of the research is not made publicly available, because that is basically like a part of some product, and they do not want to make uh, what how it is internally working to the to public, because that would affect their market and all, because other people would kind of copy them and will develop the same thing. So they want to hide some of the research which they do. So that becomes like a kind of con, because we are not able to publish and showcase our research which we do in industry to the people. So pros, so that becomes like a pro for uh, PhD and university research. So in university and PhD, whatever we do is made available to the public. So that way, we are able to get citations and acknowledgement from outside people for our work. But cons is the lack of computational resource. So in in universities, we do not have 1,000 2,000 GPUs which we get to work with in industry. So I hope I answered the question. If there is anything particular, then Chaitanya, let me know. Um, mm, Sorry, I just missed that question. Yeah. So at each step, you encountered some problem to which you proposed a solution. Is there any roadmap to this thinking to find optimum solution given the time and resource constraint? Okay. So this is from student Pilani. Yeah. So okay. So actually, yeah. So the solutions for these different problems actually are a result of like a long-term discussion. So actually, this project like it took around more than half 6 months for us to come out with this solution. So definitely and there were like multiple people involved. So as I showed in the last slide, so all of them like had big contribution for all of these solutions. So we try with like a small idea, and then we see like there are issues with it. So like people sit together, they discuss what can be tried out, what cannot be tried out. So like that we reach a solution. So it's not that we reached it, like we came up with this whole thing in a day or something. So yeah, so there is no actually like a shortcut or something. Like you have to uh, spend time and like discuss. uh, like something strikes, something doesn't work, something works. So like that you reach the solution. So research is like that only. So there is no like a one shot, one way to get all the things which you need. uh, uh, okay. Yeah, so what made me choose ISc after undergrad? Yeah, so I would say like one should go for US university. So I think so masters I think was fine at IISc, but PhD I think one can try for US universities. Uh, so I did it like for some family reasons, but definitely you should prefer US or outside, because there like you will get more exposure. Yeah. Uh, could you share your code? I could not follow this question, Prabhav. Could you share your cold mailing timeline and journey? If you can elaborate on it, then it would be great. Um, Apart from medical, so this is like from Rohan Srinivasan. Apart from medical entity, apart from medical entity linking, are there other tasks where this technique of semantic type classification to element prediction be used? Okay. Yeah, yeah. So actually, this idea is being used at other places as well. So at Microsoft, actually, I recently became a part of groups which works on a problem called as extreme classification. So they also have like a similar kind of problem, that they break a problem into two steps, where they first try to get they want to predict the cluster of labels. So basically, in extreme classification, the scenario is very similar to ours. So this is being used in ads recommendation. So for instance, like if you search something on Google, then some ads are prescribed to you. Like if you search about shoes, then Adidas shoes and Nike shoes, so those are suggested to you. So actually, this list of ads is very huge. So in total, there can be like millions or billions of ads. So this becomes like very similar to entity linking, where like any mention can get linked to any of those uh, millions of any one of those millions of concepts which are there in the knowledge graph. So similarly, in this ad recommendation also, given any query, it can get linked to, it can get not linked. Basically, for that, like we have to propose some of the ads from those millions or billions of ads. So what we do is that so I'm talking about like one of the technique. What we do is that like we cluster these ads into several clusters. So basically, like using some simple clustering approach like k-means or something like that. So we have got some k clusters uh, of those labels, millions of labels. So, for instance, we created 10,000 clusters out of those 10 million labels. Now, what we will do is that in the first step, we will try to uh, categorize uh, for that mention, for that query, what will be the relevant clusters. So suppose we have got cluster number 2 as the most relevant cluster. So now our task would be to predict the ads from that cluster. So it's very similar to what we are doing over here. So like we have broken this like large classes into some clusters, and we want to predict the cluster first, and then uh, uh, again predict among the concepts which are present in that cluster. Similarly, in this ad recommendation also, we first predict an ad cluster, and then our next step would be to select the ads which are part of that cluster relevant for that query. So like that. So this idea is actually very uh, common, and it is being used in several areas. So like it's a way of like solving classification where the number of classes are very huge. Yeah. Will you be diving into GANs for medical data generation? Okay. Um, I'm not very sure. So actually, I never made use of GAN during my research, but not very sure like how we can use GANs for it. But actually, after this work, I am also still working on this medical entry linking. So we are focusing on another aspect of medical entry linking, so that I can mention. What we are doing is that in medical entry linking, as I told, that for any given mention, we generate candidates. Uh, so that candidate can be like filtered out through our semantic type prediction. But for getting that candidate, we actually use string match. So suppose like if cold is there, so I showed that cold temperature, common cold would be its candidate. So this I'm getting because this cold, uh, like these four letters cold is common across cold mention, cold temperature, and like that. So that's why I'm generating these candidates. But one can actually use uh, deep learning for this retrieval as well. So what we do is that we represent this cold as a vector of floating point numbers, and we represent all the candidates also as the vector. And then I will propose the candidates which are closest to our mention in the embedding space. So instead of doing string match, we do nearest neighbor search in the embedding space, and that turns out to be even better. So, but yeah, your GAN question, I am not very sure like what to say about it. Like I am not like a GAN expert, so maybe we have to consult someone else. Um, how difficult is it to get a career in corporate research? Uh, so Chaitanya has asked this question: how difficult is it to get a career in corporate research? So I think it's not very difficult. So even I think after completing your graduation from BITS, you can join as a research engineer. So it's quite possible. So you can spend some time in research. So you can join this research fellowship program as well from Microsoft and Google, pre-doctoral fellowship, what they call it. They are also very. They will also give you like a very good exposure, or you can join as a research engineer at these places, and there like you'll get to work on the research problem. But for research scientist position, you require PhD, so that's the difference. But work is very similar. So yeah, it's not very difficult. You They will just ask you to have some like some understanding of machine learning. um, that yeah, so just do some internships, or like work with some like in some academia with some professor, spend some time there, and then I think it should be quite straightforward to get it. It's not very difficult, especially for bits people. It's not very difficult. Yeah. What motivated you to opt for a PhD? What are your future plans? Okay. um, yeah, so I was interested in research. Yeah, uh, yeah, so I wanted to work on like these difficult problems. So therefore, I opted for a PhD. And my future plans are to work as a scientist. So I'll join industry, and that's why I'm preferring industry over academia. So, because they are I think like you don't have to think about computational resources and other things. So yeah, so mostly I'm planning to join as a scientist in industry. So like Microsoft or other companies like that. Yeah. So I hope I have answered all the questions. In Okay, so this is another question. Sometimes in some projects, we just consider certain things as black boxes. Can you share what's your take on understanding the underlying concept? Yeah, so definitely, as a researcher, if you want to go into research, then definitely you should be knowing about what is going on inside that, because that will give you some understanding of what kind of output you are getting at the end. So although I said that I am using BERT as a black box, but I definitely know like uh, how it is working internally. So yeah, so I think this black box thing, using things as a black box, is more for engineers who are just working on some product or something and want to get something done. But if you are actually interested in research, then definitely you should not use things as black boxes, and everything should be uh, clear to you, like what's going on inside that. Can you share what's your understanding? Yeah, so yeah, so every like black box would have like some research paper associated with it, or like these people like would have described it in their documentation. For instance, like BERT has its own research paper from Google, so one can just go through it. So it's not very difficult. So in deep learning, actually, things are not very difficult. Like one can follow it very easily. So even like I think second, third year students also can follow it. uh, Things are not very complex. If you just spend some time, then like you can follow what is going on. Yeah, I hope I answered this question. So, uh, yeah,
There was one question in the message tab also.
acha. How does it know? Okay. So actually, that's what we train the model to learn. So Aditya Joshi is asking like, how does it know to relate cold and cough like in the same context? So I hope you're talking about this particular thing. So even like as a human, you can understand, right? So symptoms of something. So symptoms are of generally some diseases. So therefore, it has predicted cold as disease or syndrome. And cough, I think, is more straightforward. So symptoms of cold includes cough. So this symptom is occurring in its context. So it's very easy for humans as well as machine to figure out that this cough actually is talking about symptoms, because it is symptoms of something. So it should be a symptom only. So like that, it has predicted. But these things are learned internally. So for humans, it's obvious, but for machine, it is difficult. So therefore, like we had these big data sets. So in these big data sets, actually, these kind of things would be occurring a lot. So for instance, in this page as well, there would be something, some paragraph where it would be written that tuberculosis symptoms, like the symptoms of tuberculosis are something, 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 something. So our data set has several instances, and the model has learned to predict the correct semantic type through that instance, and therefore like it is able to work well in these kind of cases, like uh, to figure out like the correct semantic type of cold and cough, like that it is working. Yeah, yeah, so I think most of the things are answered. So
There is one new question.
acha, okay. How to read a research paper effectively within limited time? How to find appropriate research paper that help us with the problems we worked upon? So how to read a research paper within effective time, within a limited time. So yeah, I think there is no like a answer to it. So if you are like familiar with the field, then I think so if you are like working on a completely new topic, like you are reading research paper on a completely new topic, then definitely it will take some time. But if suppose like you have read like 3 4 papers already in that domain, then for a new paper actually you will be able to easily figure out like what this new paper is about, and you can like easily skip its related work section. You can easily skip the introduction, so you will just directly come to the gist and will be able to figure out like what this paper is talking about. So that's how like you can read it like quickly or effectively. So but if you're working on a completely new domain, then definitely it will take some time to understand it. And how to find appropriate research papers. Yeah, so just find one relevant paper. Suppose like you want to work on improving bird. Okay, so get this bird paper, and then you can use this Google Scholar, so which will tell you what all papers have cited bird. And Google Scholar also sorts all the papers based on their relevance. So you can look at the most relevant papers which have cited BERT. So like that you can proceed. So that like that you can find appropriate research paper once you have found out one important paper in that particular domain. So like that we proceed. Uh, so basically citation and citations is the main criteria. Like if the paper is like highly cited, then definitely one should read it, because like a lot of people are reading it, and like it contains some important things. So one can select the papers based on that. uh, yeah.
Yeah, so thank you, Dr. Shikhar, for giving your valuable time.
Yeah.
For attendees, for further question, the speaker would be present in one of the tables.
Sorry, I did not get the last line, Josh. uh,
After this session, there will be tables, and if student want to ask some more
Got it, got
questions,
it.